Hi, everyone. Welcome to the lecture on Rice's theorem. This will be a general theorem that will allow us to prove a big class of problems as undecidable. Very roughly speaking, this is what the theorem says. I'll write it formally soon. But the theorem says something along the following lines. Any non-trivial language of the following form is not decidable. If the language is the set of all Turing machines, such that M is a Turing machine and L of M satisfies some property, any language of this form is not decidable. Okay, this is roughly what the theorem says. Now I will define what it means to be non-trivial, and then we will prove this theorem. But it would immediately include several of the examples we've already seen and many other examples, basically anything that is about the language of a Turing machine. Okay, so let's start with defining this and showing this. So here's a definition. So P is a property of recognizable languages if P is a subset of the set of all Turing machine encodings. So this is one thing. It's a property of recognizable languages. So it's a property of all encodings of Turing machines. And moreover, it needs to be a property of the language and not the implementation. And for any Turing machine, for any pair of Turing machines, M1 and M2, we have that if they are equivalent, if they recognize the same language, then M1 is in P if and only if M2 is in P. Okay, so it's a property of the language of a Turing machine. Given a Turing machine, it's some property of the actual language. If two Turing machines have the same language, then they either both satisfy the property or they both do not satisfy the property. Okay, this is what it means. Any two Turing machines that recognize the same language, either both have the property or both do not have the property. Okay, so that's the definition of being a property of recognizable languages. And we will further define what it means to be non-trivial. So let P be such a property. Let P be a property of recognizable languages. We say P is trivial if P basically holds for all languages or for no language. If either P is the entire set of all Turing machines, or if P is the empty set. So it's a trivial property if the answer is always yes or always no. It always holds or not, and otherwise P is non-trivial. Okay, so P is non-trivial otherwise. So that is, just to say it again in different words, i.e. P is not trivial, it's non-trivial if it holds for some Turing machines, but not all of them. So if there exists, say, M and M prime such that M satisfies the property and M prime does not satisfy the property. Okay, and now Rice's theorem will basically say, will exactly say that any non-trivial property is undecidable. Okay, so here is the theorem. Let P be a non-trivial property, a language property of recognizable languages. Then P is undecidable. Okay, so this is the theorem, and let's see how to prove it. Okay, so we have this P. Let P be, this is P, it's some subset of Turing machines that is moreover a non-trivial property. A non-trivial property of recognizable languages. And now define, let M empty set be some Turing machine that accepts the empty set, that recognizes the empty set. So let M empty set be a Turing machine such that L of M empty set is empty set. So for example, think of this M empty set is the Turing machine that rejects every input. Okay, so assume that this Turing machine is in the language, in the property, satisfies the property. It either satisfies the property or not. Let's assume that it does, and we will prove that P is not decidable. In the case that it doesn't, otherwise, the M empty set is in the complement of P, right? And we'll continue the proof with respect to complement of P. So I'm assuming that M empty set is in P's without loss of generality, because otherwise we will just look at the complement of P. And this is sufficient because, since P is decidable if and only if complement of P is decidable. Right, we know that decidable languages are closed under complement. For example, we proved that a language is decidable if and only if both P and the complement of P are recognizable. So this would imply that P is decidable if and only if complement of P is decidable. Okay, so therefore we can assume without loss of generality that this particular machine is in P, satisfies the property, and therefore any machine that recognizes the empty language is in P. Moreover, we know that P is non-trivial, so there exists some other machine that does not satisfy P. So I don't know, I'll call it M out. I don't know what it is, but it's some Turing machine, be a Turing machine such that M out does not satisfy P. Okay, and this exists since P is non-trivial, right? So the fact it's non-trivial means there exists a Turing machine that doesn't satisfy it. Okay, so we have, let me maybe do it in a different color. We have, this is in P, and this is not in P. Okay, and so this exists since P is non-trivial, and therefore we know, also because P is a language property, we know that any Turing machine that recognizes empty set Any Turing machine that recognizes empty set is in P, and any Turing machine that recognizes the language of M out, I don't know what this language is, but whatever it is, any such Turing machine that recognizes the same language is not in P. This is since P is a language property. Great, so now we're ready to prove the theorem. Now we'll prove P is undecidable by reduction from ATM. So what is the idea? The idea is, just like the examples we saw so far, we'll assume that we have a decider for P, and we will use it in order to decide ATM and therefore reach a contradiction. So assume towards contradiction that we have some decider. In fact, when you're watching this video, perhaps you want to pause and try to think how you would prove it yourself. Okay, so assume towards contradiction that that P is decidable. This P is decidable, and let R be a Turing machine deciding P. Recall what it means. Given any Turing machine in P, R of M will output accept, and any Turing machine M not in P, R of M will output reject. That's what it means for R to be a Turing machine deciding P. We construct the following, construct S as follows. S will be a decider for ATM. So S will work as follows. So on input MW, right, that's what a decider for ATM needs to look like. S will construct a description of a Turing machine M prime as follows. So our idea is the following. We will construct some machine M prime such that if M accepts W, such that whether or not M accepts W exactly corresponds to whether or not our machine M prime recognizes either the empty set or M out. Okay, so we will engineering so that M prime, the language of M prime will be either empty set or the language of M out. We don't know what it is, but we have M out, the Turing machine, so we can run it. And which one it is would depend on whether or not M accepts W. So then we will call the decider R on M prime, and we will know which is the case. Okay, good. So, okay, so M prime will work as follows. So on input X, run M on W. So initially I just completely ignore my input and run M on W. If it rejects, I reject. If M rejects W, I reject X. But if M accepts W, I will run M out on X and output same. Okay, so this is my description. You need to, oh, last time I colored it all in blue, so let me do it again. Okay, so this is my description of M prime. S only builds this description. It doesn't run it on anything. It builds the following algorithm, which it can do because it has M and W, and it has the description of M out. So it can just do it. Run M on W. If it rejects, you reject. If it accepts, you run M out on X and output the same. Okay. So now what I will do, I will run R, the supposed decider for P, on M prime. And if it accepts, I accept. This is a decider, so it will always accept or reject. So if it accepts, I accept. And if rejects, then I reject. Okay, and I claim that this S is a decider for ATM. So let's see why. Well, if MW is an ATM, it means that M accepts W, which means let's look at what M prime does in this case. In this case, M prime on any input, no matter what the input is, will run M on W, will get to the branch of accept, and then will run M out on X. So on every input X, it will run M out on X. And therefore, the language of M prime is the same as the language of M out, right? Because it just runs it on every input. But we know that M out is not in P. So this means that M prime is also not in P because it's a language property, which means that R of M prime will reject. Okay, so let me, you see when this, I need to flip these. So the reason I know it is exactly from the analysis I see that I made a mistake. So if MW is an ATM, then R rejects, and what I would like is to accept. Okay, so I will flip it. If it accepts, I reject, and if it rejects, I accept. Okay, so this is in fact S. Okay, so if R rejects, then S accepts. And on the other hand, if MW is not an ATM, then M does not accept W. And therefore, what is the language of M prime? If M does not accept W, I don't know, it either rejects or runs forever. In any case, maybe let me write it explicitly. Let me say if M is not an ATM, then M rejects W or M runs forever on W. Which means what? It means M prime on every input X, it will either reject or will run forever in this point. So M prime rejects every input X or runs forever on every input X. On every input X. In any case, regardless of which is the case, the language of M prime is the empty set. And this we know satisfies the property. Okay, and therefore in this case, M prime does satisfy the property. And therefore R accepts, and therefore S rejects. So overall, we proved that if MW is an ATM, then S accepts, and if MW is not an ATM, then S rejects, and therefore S is a decider for ATM, which is a contradiction since we know that ATM is not decidable. Okay, and since it's a contradiction, it means that there exists no, this assumption is false. P is not decidable. There exists no R. There exists no R like this. Otherwise, this would be a decider for ATM. Okay, so this completes the proof of Rice's theorem. Let me show you the theorem again. This is Rice's theorem here, which shows that every non-trivial property of recognizable languages is not decidable. So Rice's theorem applies so applies, for example, to languages we already have seen, ETM and RegTM. Recall we saw it last week and last lecture. And in the last lecture when we saw them, we wrote a fairly complicated proof. Now, it was similar to this proof. Now, this one proof will include all future languages like that. So ETM was the set of all Turing machines that accept recognize the empty language. RegTM was the set of all Turing machines that recognize a regular language. Okay, it also applies to any other example you can think of that is a non-trivial property. So here's one other example, just to see one other example, pretty arbitrary. So consider, I'm going to prove that this language is not decidable by applying Rice's theorem. So consider the following language. M is a Turing machine. And now I want to put some property that depends on the language of M. So let's say an all strings accepted by M start with 0. Okay, so this is some property, and I'm claiming that this is not decidable. Okay, which means there is no algorithm that takes as input a program or a Turing machine and tells you correctly whether or not that program accepts only strings that start with 0 and no other strings. Okay, so this is not decidable in general. So here is a proof. We'll apply Rice's theorem. So let's call this L, this language L. So we'll apply Rice's theorem. So we need to show, or perhaps we could call it P. Let me call this P. So proof, so P is a language property. First, so you just need to show that it's a language property and that it's non-trivial. P is a language property. It's easy to see, but let me write it out. So if M1, M2 are Turing machines such that they recognize the same language, then what does it mean? Then M1 satisfies P if and only if M2 satisfies P. Why? Because all this M1 accepts only strings that start, all strings accepted by M1 start with 0, if and only if all strings accepted by M2 start with 0. Why? Because the strings accepted by M1 and M2 are exactly the same strings. So it's a language property. Moreover, P is non-trivial. There exists an M such that M is in P. Clearly, you can write a Turing machine that accepts that such that all strings accepted by M start with 0. And clearly, you can also write Turing machine that is not does not satisfy the property. Right? It's very easy to write a Turing machine that accepts some strings that do not start with 0. Thus, by Rice's theorem, P is undecidable. Okay. So more generally, you can see Rice's theorem is, for example, would be very applicable to anything you'd want to do in program verification. If you want to verify that your program satisfies some property, in general, you cannot do it. Maybe for specific programs, sometimes you can, but as a general question, this is not solvable. This is undecidable. Okay, so just to wrap up, let me mention, so this is extremely broad and strong theorem, Rice's theorem. Let me just mention when it doesn't apply, when can't you apply Rice's theorem, which is clearly when the if condition doesn't hold, but just to give you an idea, when Rice's theorem cannot be applied, well, either when it's not a property of Turing machine languages. So for example, let's say it's a property, e.g. property of, I don't know, of DFAs or graphs or equations or whatever. So if your input is not, it's not an issue of input is a general Turing machine, what does the program do? In that case, you can't apply Rice's theorem. You could potentially apply other, you could potentially still use reductions from ATM. I'll mention this briefly next time. But Rice's theorem only applies to languages that are given an Turing machine, what does it do? What does the language, what property the language has? Or if it's yes, a property of Turing machine language, or yes, a property of Turing machine, but depends on implementation. Turing machine, not just on the language. So for example, if it's something like, I don't know, a Turing machine that has at least 10 states, okay, that's easily decidable. Or you could have, what if it's a Turing machine that on every input always only moves right on the tape, never moves left. Okay, or any Turing machine where for every input W, the Turing machine takes at least 17 steps of computation. So these languages, you cannot directly apply Rice's theorem to them. You might be able to prove they're decidable or not decidable in other ways, maybe using, in some cases, Rice's theorem as one step, but you cannot directly apply if it's a property of the implementation. Okay, so this completes Rice's theorem and completes this portion of the lecture. And next time, we will talk a little bit more on how to prove undecidability, for example, of things that are not of the form of Rice's theorem. And we will also move on to discussing mapping reductions and how to prove languages are non-recognizable. Okay, thank you.